Hello, this presentation is about a long-awaited feature for the Junior programming language, that is, the steady compilation, or the ahead-of-time compilation for Julia. This is now achieved by SyslabCC, our Julia AOT compiler that eats Junior programs and produces a self-contained C++ project. We firstly introduce the problems that SyslabCC wants to address in the industrial world. Naturally, the first problem we encounter is a notorious latency in Julia. Julia has latency, the latency of startup, the latency of loading a large library, and the first time to plot a figure or just run a method that is not compiled. And there are also scenarios from the real world. SyslabCC is a tool bundled in Syslab, which is an IDE for scientific computing based on Julia. A fully load of Syslab libraries takes about half a minute. For Syslab users, modifying one line in the project with necessary dependencies takes quite a long time to pre-compile. Next, building binaries and distributions is hard and cumbersome. In Julia, delivering a program to users requires bundling the whole Julia runtime, which is a huge one. And you can do this with package compiler.jl, and the output binaries are just so big, and the building process is quite slow, which does not perform well in an iterative development process. Another notable issue is about calling the shared libraries from Julia. You can use package compiler to produce a shared library to ease the latency issues for specific packages, but the output libraries cannot be loaded again into the Julia process anymore. The third problem is about the deployment. We just cannot deploy Julia programs to many target devices in the production environment. We want to write scientific programs in Julia, and then we debug them, we test them, and finally run them under 32-bit ARM devices in a robust workflow. There have been some excellent works based on steadycompiler.jl, but it is still far from supporting a large number of the commercial libraries we have created in Julia. So not everyone is a Julia expert and not everyone can write allocation-free code. Instead, most engineers just write algorithms, and we want to make things smooth for engineers. So that's a background for SyslabCC. On the first day of this year, we managed to create the first edition of our Julia AOT compiler to address above mentioned issues, and it has been iterated for a few months and has been verified by several real-world scenarios. We highlighted this example where we use the Junia's rich ecosystem to achieve automatic differentiation. As can be seen from this example, we firstly load the AD library Zygote and define a function f and compute its derivative according to the user input. No chaining rules and no tracing, and everything is simple and automatic with best performance, and that's it. SyslabCC compiles this script, producing binaries that is latency-free and standalone and small and portable, and this is indeed the state of the art. In the latter part of this presentation, I'll introduce you the exciting features of SyslabCC plus the compatibility with the Julia ecosystem, the performance, the limitations, and the details of internal designs. And this is actually the feature list of SyslabCC. We have heap allocations, we have the full exception handling, we have macros, we have multiple dispatch, compile time, commutations, and C interoperability. Actually, we support the type-stable subset of the Junior programming language. We then come to the key features in the next few slides. So as can be seen from this example, we have heap allocations managed by a real GC, which leverages the well-known BDWGC under the hood. So this example adopts code directly from benchmarks game, except adding the main function. We have also detailed benchmarks against the native Julia and GCC, which I'll introduce later. This example is also, an extreme and worst case for GC allocations with our AOT compiler. But in the earlier versions of SyslabCC, we are much slower than the native Julia in this case. But now there's never such a gap. You see the performance is very similar, and we also have full exception handling. We write such, in this case, you can currently write try and catch and finally blocks in your AOT programs. If they are valid Julia code, they are well handled by SyslabCC. Besides, I'm proud of writing the transformation from the Julia 5C nodes, and upsync nodes into our own intermediate representations. So SyslabCC also supports the complete surface syntax for Julia. The valid Julia code usually passes and compiles in SyslabCC if they are type stable. And this is because our works are based on the Julia type code info, which is made after passing type inference and multiple dispatch. That is the method resolution or instance resolution, as we have as we have multiple dispatch function calls get specialized and introduce no overhead. Multiple dispatch works together with constant propagation and inline expansion. This means that advanced patterns like holy traits are well supported in SyslabCC. And we also have special thanks to the Julia compiler team. The compiler pipeline is really reusable and really reusable. This compiler's reusability is not just a concept in theory. It's practical. It's practical. And we also have full support for the compile time computations and syntactic macros. It's because SyslabCC compiles after macro expansion, so you can write down arbitrary. You can just write down the arbitrary Julia code and run them in the top level of your module. And this example is very interesting. You train the model, the deep learning model with flex.jl and CUDA.jl, and then export the model to C++ with SyslabCC, and finally we have such a high performance inference model in the generated C++ code, which compiles and runs everywhere. And another key feature is that the Julia constants are also supported by the AOT compiler, not only for trivial types like integers or floats, but also for heap allocated objects such as arrays, dictionaries, and user-defined types. As far as I know, there's a key feature for areas like deep learning and traditional simulations where the whole model with Julian parameters can be directly saved into the generated C++ code. And we also support C interrupts. We support C code to call function pointers from a shared library, and we support the macro C function to create function pointers from a given Julia function object. With this feature, you can load arbitrary shared libraries. Your Julia program just goes relatively smoothly, cooperating with any existing C or C++ code base. So this page will show the ecosystem compatibility of SyslabCC. As can be seen, the status is pretty promising. The major restriction of our AOT compiler is that you need to make sure the code is type stable. But although SyslabCC requires strict type stability, it does work well with the ecosystem. We support a large number of standard libraries, including base, linear algebra, printf, and so on. And of course, standard libraries have execution paths that are not yet type stable, so we are now actively working on making patches for such cases without modifying the existing code. We have some mechanisms to do this, and SyslabCC also funds an elegant and systematic way to AOT compile your Julia programs. We know we have done the right thing, and without much effort, SyslabCC now works for the following libraries: base, in the algebra, printf, fftw, static arrays, and many others. And we also, the exciting thing is that we also support Zygote. Zygote provides an easy-to-use automatic differentiation, but suffers from the latency issues in the native Julia. But with SyslabCC, you can just compile the derived functions in need into a shared library and load them into a regular Junior program to avoid the huge latency of loading Zygote in your major workflow. This means that your project does not need to depend on Zygote anymore. It just use AOT compiler, use SyslabCC to produce a shared library uh, with Zygote, and then your major workflow, your project just reference the shared library and call the draft functions from the libraries, and they are just function pointers, and we also support data structures.jl. This is also exciting because this literally means you use a large number of generic and high performance advanced data structures in C or C++. And this support list is incomplete, and I think the regular junior programs that guarantees type stability should work well with SyslabCC. And there are also instructions. The dynamic dispatch, LLVM core, and threads modules are not supported yet. So let's go to the next topic. It's about the performance. About the performance, the first thing we need to clarify is that the AOT programs has low latency, a low startup latency, low first time to X latency, so the program runs instantly and performance is quite good. We have tested SyslabCC against the well-known benchmark scheme cases. For computation-intensive cases like n-body and n-cream, the single-thread performance of SyslabCC strictly matches Junior, C, or C++. Besides of the benchmark, we also have large-scale cases. We have compared SyslabCC with established code generators and the simulation software, observing a 20% performance improvement in the user scenarios. It seems not a great number, but it's just a start, and we have restrictions. In theory, Junior runs magnitudes faster than Python, Octave, or similar programming languages, but the libraries implementing the legacy functionality in Julia are usually not produced by Junior experts. And even in this case, the AOT Junior program can still outperform C code produced by established solutions. And due to the commercial confidentiality, we cannot disclose more comparison details, but it is free for you to apply a non-commercial license. You can apply a non-commercial license and test it yourself. So we then talk about the limitation of SyslabCC. The first limitation is about multi-threading support. The current exception model is limited and may get missed in your multi-thread environment. We are actively working on this, and hopefully we will make it before August. And we will finally support threads module, and you can also use the C++ solutions at the current stage. And the second limitation is about the LLVM core. Currently, we don't support LLVM core in SyslabCC, but there is nothing prevent us from supporting it, but there is still, a whole host of the higher priorities. And the last limitation is distinct, and it's fundamental limitation. It's about the asynchronization model. Julia uses libuv, and the async model uses symmetric coroutines under the hood. And it's possible to use libuv or implement our own symmetric coroutines using uContext or fibers in C or C++, but it requires a bunch of works to maintain libuv or just write platform-specific code in C or C++. But the major goal for SyslabCC is generating highly portable code with minimal platform requirements, so that it will work for embedded systems like 32-bit ARM devices. As a result, we dropped the support for Julia's async module, but we are still compatible to the common async functions in Julia. For example, file I/O operations and printings are async in Julia, but they are actually synchronous in SyslabCC. So how could we achieve this? We actually managed to provide compatible C codes for libjulia. We cannot depend on libjulia, but we just replace the C codes. We implement our own with C++, and then we replace the print. We also replace the print function with a set of type stable Julia methods. They are not async anymore, but they are fast enough and reliable. And as for the dynamic dispatch, we don't talk about it today because things are still under active investigation. And finally, let's come to the internal design of SyslabCC. As I said before, the whole work is based on Junior's typed coding for, uh, and we do not rely on code.compiler called .ir code. This is because we want to avoid something that are not that stable, and we want to avoid some Junior specific stuffs. If we have, consider we have a Haskell compiler expert, and this guy will not be very familiar with this representation, so we want to make things simple. And then we transform typed code info into our own one. We call it the normalized IR, and the latter one is guaranteed to be stable across different Junior versions and is processed in a statically typed programming language. We actually crazily improve the maintainability and efficiency using exhaustive pattern matching and algebraic data types, ID toolings, etc. And we then work on our own IRs and finally produce a C-like representation. This architecture is flexible. It's very flexible because it will allow us to generate code for multiple targets, including C++. And C++ is now the only public target. And we recursively process Junior function calls and create C++ functions and types out of the function calls. And the leaf function calls in the code graph are either intrinsics or C functions from libjulia. So we finally implement them in C++ without LLVM. And this is very, difficult because Junior is based on LLVM, and LLVM IR is actually a strict sub is a LLVM IR is a strict superset of C. So Junior uses LLVM intrinsics that are not available in standard C, so we either lose the chance to call the base hardware instructions, or we have to call the specific compiler extensions like GCC extensions. And we currently use the GCC extensions, but for very old GCC distribution where the compiler extensions are not available, we roll back to the software implementation as an alternative, which is actually much slower. So that's the deal of our current works. The future plan goes here. Our next focus is to support newer Julia versions, and Julia is evolving, and we have good consideration about the involving at the very beginning. As you know, for example, we have the normalized IR. It's designed to work for different versions of Julia, and then we will improve the support to multi-threading scenarios. We will support the various locks in Julia and compat the basic usage of base.threads module and fixed through exceptions in multi-threading environment. And we will also support creating binaries that calls GPU features. This is also in our plan, and in the rudimentary assessment, CUDA.jl could be supported without pain by supporting LLVM calls. This means that if we support LLVM calls, we can support CUDA.jl, and then we can access GPU features without installing Julia. So you can see more details in this architecture. This architecture, and finally we I want to say that thanks here, thanks for being here, and I have special thanks to the whole Junior ecosystem and the package developers, and I appreciate it a lot for the rich ecosystem. And I also have special thanks to the junior compiler team for the reusability of the compiler pipeline. And personally, I have special thanks to the junior developers in Tongyuan, especially for members. I mean, for members in Syslab PLT and math team and the secret precision team and the taste team. So you can find the code examples with the GitHub link at the bottom. Here the bottom. So thanks everyone for being here again, and that's all.